Hi, Tutor Tori here to answer all your guys' questions about these two creative young ladies who have submitted a proof for the Pythagorean theorem for peer review. At the end of this video, I'll show the proof. The school is St. Mary's Academy in New Orleans. The usefulness of finding additional proofs for something that's already been proven is like looking at a city that already has a road leading to it and deciding to build more roads that lead to that city from other places. That way, anytime you're trying to do anything in math that requires you to pass through that city, you can pick the most convenient road. Mathematicians, let me know if you consider that an accurate analogy. For this reason, there are hundreds of proofs for the Pythagorean theorem, and they're easy enough to come by that the school included it as the bonus question in their math challenge. It does not warrant an automatic PhD, a Nobel Prize, or a Fields Medal, though I love the enthusiasm. To discover a new Pythagorean proof of any kind is exciting and laudable. To do so at the age of 17 is remarkable. But what really impressed people about the girls' work was a statement made in a 1940 book by mathematician Alicia Loomis, who cataloged over 344 proofs of the Pythagorean theorem by type, and then claimed that no trigonometric proof was possible. To me, achieving a thing that is thought to be impossible is groundbreaking. I didn't know that in 2023, it's not thought to be impossible, because since the time of Alicia Loomis's book, trigonometric proofs have been discovered. Thank you so much to the at least 4 commenters who let me know this. One of these trigonometric proofs was derived by mathematician Jason Zimba, one of the co-creators of Common Core. He directly references Alicia Loomis's claim that there are no trigonometric proofs of the Pythagorean theorem, saying that this particular trig identity right here actually can be derived independently of the Pythagorean theorem and therefore can be used to prove it, which he then proceeds to do in the peer-reviewed scientific journal Forum Geometricorum. This proves Alicia Loomis wrong and answers the first of our 2 questions. No, this is not the first trig proof of the Pythagorean theorem. Our second question about whether this is a valid new proof will be answered by the peer review. And now, the moment we've been waiting for. YouTuber Math Train explains that the reason I was unable to find their proof to show you in the first video I posted was because it won't be available until the peer review is complete. However, he was able to use footage from their presentation at the American Mathematics Society to come up with a series of calculations on his own that he believes must be their proof.
We of course start off the same way every Pythagorean proof starts, by drawing a right triangle, A, B, C as the sides. Then once we've labeled our angles beta and alpha, we are going to do something a little different. We're going to extend a line out from the tip of angle beta perpendicular to the hypotenuse of the triangle. And then we're going to make a mirror image of the original right triangle. We're going to notice that this angle is alpha, and then we'll extend the hypotenuse of the second right triangle that we drew until it intersects with this other line. From the original right triangle, we've now constructed a new larger one with sides x, c, and z. The last part of this construction is to subdivide this big triangle into infinitely many smaller right triangles, which are all similar to the original that we drew. The construction is finished now, so let's start calculating. This is supposed to be a trigonometric proof, so let's throw in some trigonometry. The sine of an angle does not depend on the Pythagorean theorem in any way. While it is highly related, you can define the sine of an angle without having any reference to the Pythagorean theorem. It's effectively just an application of similar triangles and their proportions. That being said, you can easily calculate the hypotenuse of this triangle to be 2a divided by the sine of beta. Looking at the original right triangle, the sine of beta is b divided by c, and therefore we simplify this to 2ac over b. Multiplying then by the sine of alpha, we get this expression for the other remaining side, and then dividing by the sine of beta, we can get the expression for the hypotenuse of this smaller triangle. Johnson and Jackson note that the ratio between successive triangles as you go further down this infinite descent is a over b for each triangle, meaning that on both sides, each successive hypotenuse gets multiplied by a squared over b squared, since you're going 2 triangles down the line. This is going to create 2 geometric series, each with the same common ratio, a squared over b squared. So x can be calculated using that exact geometric series, as you can see on the right here, factoring out a factor of 2ac over b, and then noticing that the common ratio r is a squared over b squared, we can evaluate the length of the side x. In this expression, since r was a squared over b squared, we can go back and go on algebra autopilot to simplify x down to this expression. Let's put that aside for later. As we evaluate the expression for z, we notice that we have to add a c in front of it, followed by a geometric series. Take a moment to check the algebra for yourself if you like, and I'll leave it as an exercise again to substitute in a squared over b squared for r, and simplify z down to this expression, which is very similar to the expression we got earlier for x. So similar, in fact, that if we take their quotient, these 2 factors will cancel out, and we'll be left with just 2ab over a squared plus b squared. And then comes the realization that x over z is just the sine of 2 alpha, opposite divided by hypotenuse for this 2 alpha angle here. Jackson and Johnson then make the ingenious realization that the law of sines has no dependence on the Pythagorean theorem, and therefore we can apply the law of sines to this situation. Looking at the triangle formed by our original small triangle and its mirror image, we can see that the sine of 2 alpha over 2a is equal to the sine of beta over c. Simplifying that gives us an expression for sine of 2 alpha. But the sine of beta on the right-hand side is just b over c, and so we can simplify this even further. Now we have two suspiciously similar-looking expressions for the sine of 2 alpha, and therefore their denominators are equal. In other words, almost out of nowhere, a squared plus b squared equals c squared. While I'm not sure if this is exactly how Jackson and Johnson did the proof, the one that I showed should be pretty similar based on the news reports that I saw. The only major theorems I saw this relying on were the angle-angle theorem and the law of sines, both of which have proofs which are completely independent of the Pythagorean theorem.
To all the commenters who said,
I wish I were high on pot news.
it's not cool to steal other people's jokes. Thanks for all your questions and for working together to get to the bottom of this. Follow and share.